Hi everyone, today's lesson is on the Pythagorean Theorem and the converse of the Pythagorean Theorem. So the first thing we're going to talk about is the Pythagorean Theorem. I'm sure you've heard about it before, but if you haven't, the Pythagorean Theorem is a theorem that specifically works with right triangles. So here we have a right triangle. The two legs we are going to call A and B, and the hypotenuse, which is the longest side of a right triangle, is labeled C. So your hypotenuse is always going to be across from your right angle. So the Pythagorean theorem tells us that in a right triangle, a squared plus b squared is going to equal c squared. So let's do a couple examples of using the Pythagorean theorem to solve for a missing side of a triangle. So in number 1 here, we're given the two legs. Our two legs are 9 and 6. So this is my A, this is my B, and we're looking for that hypotenuse x, which in our Pythagorean theorem is the variable c. So we're going to take these numbers and just plug them straight into our formula. So 9 squared plus 6 squared equals x squared. I'm going to evaluate those powers. So we have 81 plus 36 equals x squared. And we get 117 equals x squared. Now to solve for x, we're going to take the square root of both sides. Now, if this was an algebra problem, we would say that x equals plus or minus the square root. But because this is a geometry problem, we're talking about the side length of a triangle. We know it has to be positive. So x is going to equal the square root of 117. If we simplify that radical, we can break this up into the square root of 9 times the square root of 13. So x equals 3 times the square root of 13. All right, number 2, we have the hypotenuse here and we're missing one of our legs. So we're still going to set this up the same way. We have 7 squared plus x squared equals 9 squared. So 7 squared is 49 plus x squared equals 9 squared, which is 81. I'm going to subtract 49 from both sides so that I get my x squared alone. And x squared is going to equal 32. Take the square root of both sides, and x equals, this is going to be the square root of 16 times the square root of 2 if we're simplifying our radicals. So x equals 4 times the square root of 2. And again, because we are talking about the side length of a triangle, we only care about that positive value. All right, so a couple more examples for number 3. We're looking for a leg, so x squared plus 8 squared equals 12 squared. So we evaluate those powers. We're going to subtract 64 from both sides, so x squared equals 80. And x is going to equal the square root of 80. I can break that up into the square root of 16 times the square root of 5 if I'm simplifying my radicals, and I get 4 times the square root of 5. Okay. Number 4, again, this is similar. We're looking for the leg. So x squared plus 8 squared equals 16 squared. 64 plus x squared equals 16 squared, which is 256. Subtract 64 from both sides, and we get 192. And again, when we take the square root of both sides, if we're simplifying that radical, we're going to have the square root of 64 times the square root of 3. The square root of 64 simplifies to 8s. The square root of 3 can't be simplified. All right, so that is our final answer. Okay, number 5 here, we have one of our legs is 40, one of our other legs is 9, and we are just looking for that hypotenuse. So 40 squared is going to be 1600 plus 9 squared is 81. All right, and we are going to get x squared equals 1681. All right, this looks like a really large number that's going to be hard to simplify, but this is actually a perfect square, and x is just going to equal 41 here. Okay, now this is called a Pythagorean triple. So a Pythagorean triple is going to be any three sides of a triangle or of a right, any three sides that form a right triangle that are integer values. So you're not going to have decimals, or you're not going to have this simplified radical form. So some of our more popular Pythagorean triples are 3, 4, 5, 5, 12, 13. But if you know them, it's just kind of nice to know. It makes the math work out a little bit quicker. So moving on to our last example here, number 6, we are given 2 legs. We're looking for that hypotenuse. So 4 squared plus 6 squared equals x squared. And we get 52 equals x squared. And again, we're going to simplify that radical here. You could just plug this into the calculator and get a decimal value if that's what your teacher allows. But if you want to simplify your radicals here, I look for that perfect, or that largest perfect square, which in this case would be 4. 4 times 13 is 52. So the square root of 4 is 2, and then I leave that square root of 13 as is. Okay. Now we're going to look at some word problems here with the Pythagorean theorem. So for number 7, it says a ladder is standing against your house. If the ladder is 4 feet from the base of the house and reaches up to the window 13 feet above the ground, how long is the ladder? Round to the nearest tenth. So we're going to want to draw a diagram here to kind of help us. All right, so here is our ladder. We're trying to find out how long the ladder is, so we're going to call that x. This ladder is leaning against a house, so the house and the ground are going to form a 90-degree angle. That's what's making this a right triangle and allows us to use the Pythagorean theorem. And we know that this ladder is 4 feet from the base of the house, and it reaches up to a window that is 13 feet above the ground. Okay, so now that I have that triangle drawn, this looks like one of those Pythagorean theorem problems we did up there. So 4 squared plus 13 squared equals x squared. So 4 squared is 16. 13 squared is 169. So we're going to get 185 equals x squared. Take the square root of both sides. Now again, this is something that kind of just depends on what your teacher wants, but for word problems, I don't have my students use simplified radical forms because if I saw something like 4 root 5 in a word problem, I don't really know what value that actually is off the top of my head. So I plug the square root of 185 into the calculator, and I'm going to get 13.6 feet as my final answer. Okay, and then our last problem, or our last word problem, number 8, it says televisions are measured by their diagonals. If a 65-inch television has a height of 32 inches, will it fit on a TV stand that is 52 inches long? Show work to support your answer. So this one's a little bit tricky. So we're going to have this TV here, and if you didn't know, like it says in the problem, TVs are measured by their diagonals. So if I had a TV with a diagonal of 65 inches, that would be a 65-inch TV. It tells me that there is a height of 32 inches. Okay, and again, this would be a right triangle if it's a TV and a rectangle. So what I want to know is if this will fit on a 52-inch long TV stand. That does not mean that the width of this TV is 52. I want to find the width of this TV and then compare it to 52 inches. So I'm going to call that value x. So I have my Pythagorean theorem right triangle set up. X squared plus 32 squared equals 65 squared. So x squared plus, so 32 squared is 1024. 65 squared is 4,225. So I'm going to subtract both sides by that 1024. So x squared equals 3,201. If I take the square root of both sides, x is equal to 56.6. So that means the width of this TV is 56.6 inches long. If the TV stand is only 52 inches long, then no, it will not fit. So we can say no, the TV won't fit on the stand. So we answered the question and we showed some support or some work to support our answer. Okay, now that is the Pythagorean theorem. Now let's talk about something called the converse of the Pythagorean theorem. So the converse of the Pythagorean theorem is a way to look at three sides of a triangle and determine if that triangle is right, acute, or obtuse. Okay, so this is called the converse of the Pythagorean theorem. Now let's start with the one that's a little bit more obvious. If c squared equals a squared plus b squared, which is our Pythagorean theorem, then we can say that the triangle is a right triangle. Okay, so we're using that Pythagorean theorem and we're just working backwards. If we have an acute or an obtuse triangle, instead of c squared being equal to a squared plus b squared, it's going to have a different relationship. So the reason I'm putting this c squared here, we'll talk about that in a second when we see those inequality symbols. But in an acute triangle, c squared is going to be less than a squared plus b squared. Okay, so again, if it's an acute triangle, c squared is less than a squared plus b squared. If it's a right triangle, c squared is going to be equal to a squared plus b squared. And if it's an obtuse triangle, c squared is greater than a squared plus b squared. Okay, now the reason that I like to write c squared first is because when I'm thinking of an acute triangle, I'm thinking of acute angles, which are all less than 90 degrees. So I'm already thinking of that less than inequality symbol. When I'm thinking of an obtuse triangle, I'm thinking of an obtuse angle, which is greater than 90 degrees. So I like to put the c squared first, so those inequality symbols match what I'm already thinking about. So for my directions here, it says given the lengths of the three sides, determine if the three sides, this should say form an acute, right, or obtuse triangle. So the first thing we need to do is use that triangle inequality theorem to make sure that our three sides form a triangle to begin with. So remember, the triangle inequality theorem tells us that 21 plus 28 has to be greater than 35 for this to even form a triangle. So I'm going to check here, and the length of my two smaller sides, when I add them together, is greater than the third side. So I know this is a triangle. So now I'm going to jump into that Pythagorean theorem converse. So my largest side is going to be my c value. So 35 squared. I'm going to put a box or a circle there because I don't know what symbol is going to go there. I don't know if this is going to be a less than, an equal to, or a greater than symbol. 21 squared plus 28 squared. All right, these are pretty big, so you might want to plug them into a calculator. So I have 1,225. 21 squared is going to be 441, plus 28 squared is 784. Okay, so I'm going to add the right side to get 1,225. I'm comparing that to 1,225, and those are equal. So because I have an equal sign, this is going to be a right triangle. This is another example of one of those Pythagorean triples that I was talking about earlier. Let's check number 10. Okay, so for number 10, I have my two smallest sides, 10 plus 17, and I want to make sure that's bigger than my third side. So 27 just makes it, that is greater than 26. So I know this forms a triangle. So I'm going to move on and check to see what type of triangle this makes. So 26 squared is going to have some relationship to 10 squared plus 17 squared. So 676 has some relationship with 100 plus 289. So once I simplify that right-hand side, I have 676. That is going to be greater than 389. So because my c squared is greater than a squared plus b squared, this is an obtuse triangle. Okay? I'm going to go in detail for the next two questions. So for number 11, first I want to make sure that this is a triangle. So 2 plus 10 is greater than 13. Now, when I do this, I get 12 is greater than 13. I know that's not true. So I actually don't have to go any further. This is not a triangle. If I try to make a triangle with these three sides, the triangle inequality theorem tells me that I cannot do that. So we're going to move on to number 12. So number 12, I have 10 plus 11. I check to make sure that this even forms a triangle. And in this case, it does. I get 21 is greater than 14. So now we're going to check to see what type of triangle we have. So 14 squared is 169. It's greater than 100 plus 121. So 196 in this case is going to be less than 221. So if we go back and look up here, if c squared is less than a squared plus b squared, like in number 12, this is going to be an acute triangle. Okay, so these four examples here are each of the four scenarios that you could get. You could get a right triangle, you could get an obtuse triangle, not a triangle, or an acute triangle. Okay, I'm going to go through the next four a little bit quicker because we've kind of seen an example of each one of these. So for number 13, my two smaller sides, 5 plus 6. All right, I check, and that is greater than 9, so we're good to go. So 9 squared has some relationship with 5 squared plus 6 squared. All right, now 5 squared plus 6 squared, that is going to be 61. So I kind of jumped and skipped some steps here. I have a greater than symbol, so this is going to be obtuse. Okay, number 14, this one is actually not going to be a triangle. So 5 plus 7 is 12. 12 is not greater than 13, so this is not a triangle. Okay, for number 15, this is a triangle, so I have 26 is greater than 24. We're good to move on. So 24 squared is going to have some relationship to 8 squared plus 18 squared. All right, 8 squared plus 18 squared is 388. This is a greater than symbol, so we have another obtuse triangle. And our last example, we have 6 plus 8, that is greater than 10. So 10 squared has some relationship with 6 squared plus 8 squared. 6 squared plus 8 squared, you can plug that straight into a calculator. you're going to get 100. So because 100 equals 100, this is a right triangle. All right, so that is your Pythagorean theorem converse. Again, your Pythagorean theorem tells you that if you have a right triangle, a squared plus b squared equals c squared. And the Pythagorean theorem converse tells you if you have your three sides, you can use these three relationships here to determine if it is an acute triangle, a right triangle, or an obtuse triangle. Thank you so much for watching. If you have any questions, you can comment below. Thank you.